quality determines the success or failure of a fish cultural operation. Physical and chemical characteristics such as temperature, salinity, light, turbidity, dissolved oxygen, pH, alkalinity, hardness, ammonia, nitrite, nitrate, carbon dioxide, hydrogen sulfide, and heavy metals. All the above parameters should be in optimum levels or limits. Heavy metals should be within the levels below their upper limits. For gases, oxygen must be kept above the minimum of 4 or 5 ppm, while other gases must be below critical lethal concentrations in hatchery. Temperature is the most important physical factor to consider in aquaculture because of its influences in the aquatic environment. No other single factor affects the development and growth of fish as much as temperature. It is the intensity factor of heat, which is measured by a mercurial thermometer, yellow spring instrument, or other means. Temperature fluctuation should be minimal. Abrupt change by greater than or equal to 5 degrees Celsius is stressful or lethal, so care must be taken. The following are the effects or influences of temperature. First is that it affects the metabolic rates of organisms. Rate of respiration increased with increasing temperature, and dissolved oxygen consumption increases with increasing temperature. Second, it affects solubility of gases. Solubility of oxygen is less at high temperature compared with lower temperature. Third, it affects the stability of water column, which means that there is no uniformity of temperature in the water columns. The non-uniformity of temperature in the water columns is known as the thermal stratification or layering. Warmer water is at the upper column, except when temperature drops to below 4 degrees Celsius, where warmer water is at the lower column. Fourth on the list is that it influences growth of aquatic organisms such as plants and animals, including fin fishes and shellfishes. At the ideal range of 27 to 29, fish growth is accelerated with high survival. Lastly, for fifth, it influences spawning and shortens the time of hatching. At higher degree in the ideal range, spawning and hatching are hastened or accelerated. Temperature outside the temperature tolerance limits ranging from less than 21 and greater than 35 will impart stress and disease and eventually will cause mortality. Factors influencing increase of heat in water includes dissolved substances, suspended particulate matters, and plankton. For example, in fish pond, the water temperature at the surface is equal to 31 degrees Celsius before the start of a bloom of plankton, and becomes 35 degrees Celsius at the height of a bloom, based on an observation. From this fact, it could be generalized that the greater the density of plankton, the more light is absorbed at the surface and consequently much heat is generated in the aquatic environment. Salinity is the measure of the total concentration of all dissolved salts present in a natural body of water expressed as grams of salt per kilogram of water. The term salinity does not restrict itself to the levels of sodium chloride present. Although this accounts for a major part of it, the term salinity also includes all other dissolved ions such as potassium, magnesium, calcium, and sulfate ions in smaller concentrations, as well as trace amounts of many salts. Aside from gram per kilogram, salinity is also expressed in various units or ways as follows. First is parts per thousand, second is per mil, and lastly percent. Various techniques or methods in measuring salinity. First is the density technique, which is the least expensive. Recorded density is converted to salinity by employing conversion table. Instrument used to measure density is a hydrometer. Second is a refractive index of seawater method, which is the simplest and most rapid method. It directly measures the salinity of water. Instrument used is a refractometer, which is quite expensive. Third is the conductivity method, which is the method of high precision. The device used in this method is much more expensive and yet requires a fairly large sample. It is useful more often to the researchers than the aquaculturists. Fourth and lastly is the titration method. This requires reagent solutions such as chemicals and is done in the laboratory with the aid of a burette, Erlenmeyer flask, and etc. But note that the first two methods are to be used when salinity is suspected to be high. Classification of aquatic environment on the basis of salinity. For fresh water, having less than 0.5 parts per thousand salinity. For brackish water, having 0.5 to 34 parts per thousand salinity. And for marine water, having greater than or equal to 35 parts per thousand to less than 40 parts per thousand salinity. There are two factors that affect salinity of marine coastal water, namely are rainfall and freshwater runoff. Rainfall directly and indirectly reduce salinity of coastal marine water, while freshwater runoff from rivers greatly reduces the salinity of coastal marine water, and so culture sites should not be immediately adjacent to the mouth of the river. Effects of salinity. First, it affects solubility of oxygen. Dissolved oxygen decreases with increasing salinity and vice versa. For example, at the same temperature of 30 degrees Celsius and 0 parts per thousand salinity, dissolved oxygen is 7.6 parts per million. For 30 degrees Celsius and 10 parts per thousand salinity, dissolved oxygen is 7.1 parts per million. For 30 degrees Celsius and 20 parts per thousand salinity, dissolved oxygen is 6.8 parts per million. And for 30 degrees Celsius and 30 parts per thousand salinity, dissolved oxygen is 6.4 parts per million. For the second effect, it affects the osmoregularity function of most aquatic vertebrates including fish. Osmoregulation requires a significant amount of energy to maintain the fish body fluids to counteract the effect of salt concentration of the habitat that may lead to mortality. Third and lastly, fluctuating salinity, especially a sudden change such as a decrease or an increase of at least 5 parts per thousand salinity, greatly causes stress or even death of fish.
Light is a radiant energy, and the sun serves as its ultimate source. The sun emits light across a spectrum of wavelengths, including visible light, which is important for sustaining life on Earth. Light penetration into aquatic systems is influenced by the angle at which sunlight enters the water. At lower angles, less light is absorbed and more penetrates into the water, whereas at higher angles, more light is absorbed, allowing deeper penetration. Lower angle sunlight tends to be less absorbed, resulting in more scattering, diffusion, and reflection of light back into the atmosphere. Light absorption plays a crucial role in the response of phytoplankton to the application of inorganic fertilizers. Phytoplankton, being primary producers, rely on light energy for photosynthesis. When light absorption is greater, such as during periods of higher solar angles, phytoplankton can more efficiently utilize nutrients from fertilizers, leading to increased growth and productivity. Light gives the energy needed for primary productivity, or PP. This process is called photosynthesis. Illuminating dark water helps aquatic animals see their food for brightening up dark water. making it easier for them to locate and capture their prey. This is a direct effect of light. The presence and intensity of light affect the types and quantities of food available for fish. Light influences the growth of plants and algae, which serve as food sources for many aquatic organisms, including fish. So, light indirectly determines the food options for fish. Light also plays a role in the coloration of the bodies of aquatic animals. Some organisms may have adaptations in their coloration that are indirectly influenced by light conditions in their environment. Light can also trigger and guide the movements of aquatic animals. For example, some species may migrate or change their behaviors in response to changes in light, such as dawn and dusk. This effect of light on animal behavior is direct and can influence their feeding, mating, and other activities. There are three factors affecting absorption and penetration of light in the lower zone of the aquatic system. Firstly, the dissolved substances in water, like minerals and gases. It can change how light moves through the water. If there is a lot of colored stuff dissolved in water, it can absorb light and make it hard for light to go deeper. Secondly, are the suspended solids or particulate matters. Tiny bits flowing around in the water like dirt or algae can scatter and absorb light. If there are a lot of these particles, they can block light from going deeper into the water. Microscopic plants and animals in the water can also absorb light for their own use. When there's a bunch of them, they can soak up a lot of light, making it harder for light to reach deeper parts of the water.
Turbidity. Turbidity is the measure of relative clarity of a liquid. It is the transparency of water that is reduced by dissolved substance, suspended solids, and plankton. And there are specific factors that causes turbidity. First is soil erosion, mining waste, sewage and sewerage effluent discharge, microbial breakdown of organic matters, and planktons including phytoplankton and zooplankton. There are also effects of turbidity, including restricting light penetration, thereby limiting photosynthesis and the production of desirable plankton in ponds or tanks, gill damage on fishes, smothering of fish eggs, and destroying of benthic organisms in ponds, example, lab, phytoplankton die-off, dissolve oxygen depletion, render difficulty for fish to find food, sedimentation, and clogging of hatchery pumps, filters, and pipelines. There are remedial measures in precipitating clay turbidity. For small areas like ponds and tanks, application of gypsum, as reported, an application rate of 20 mg per liter or 20 ppm of gypsum can decrease 91% of the turbidity without endangering fishes and other aquatic organisms. Application of agricultural lime at the rate of 500 to 600 kg per hectare can also reduce turbidity by precipitating the suspended solids, and rice hay at the rate of 500 kg per hectare was found to reduce turbidity. Turbidity is measured either by the following instrument or devices. First is turbidimeter, which is expressed in parts per million, used in muddy waters that is usually contains less than 2,000 parts per million, and clay turbidity in natural waters rarely exceeds 20,000 parts per million. Next is Secchi disc. This is a circular metal or wooden device painted alternately black and white attached to graduated pole or rope and is expressed in linear measurement, for example centimeter or meter. This device measures the transparency of water or the distance of visibility of the Secchi disk from the water surface measures the turbidity of such water. However, if turbidity is referred to as the abundance of plankton production, then the distance of the visibility of Secchi disk multiplied by 2 is equal to the depth of euphotic zone, which is the production zone. In fish pond, the depth of measurement or thickness of euphotic zone is usually less than 1 meter. Third is the weighing balance. This device is used to weigh the precipitates in milligrams, grams, or kilograms, which are obtained from settling down the suspended solids or particulate matters. In general, turbidities less than 2,000 parts per million are acceptable for fish culture. As to the use of the Secchi disk, the ideal disk reading is less than 30 or 40 centimeter.
Dissolved oxygen. Dissolved oxygen is the gas of greatest importance in fish culture. It is a highly critical water quality parameter in fish culture. It is important for the fish culturist to fully acquaint himself with the dynamics of dissolved oxygen's concentrations in pond, lakes, and other aquaculture systems, including tanks of different types. So here are the uses of dissolved oxygen in aquaculture. It is used for respiration. It helps in feed consumption, digestion, and assimilation. It maintains osmotic balance of fish. It helps in fish activity such as swimming, searching of food, and the like. And lastly, it helps in the oxidation of metabolites in the aquatic environment such as the ammonia and hydrogen sulfide into usable form nitrate and sulfate respectively. Now let's move on to the factors that influence oxygen production in water. First, we have the light availability. Next, magnitude of chlorophyll bearing or green plants, concentration of nutrients, and last is the temperature. At near freezing point and greater than 40 Celsius, plants cease to do photosynthetic activity. Declines when oxygen holding capacity of water. It is warm or its temperature is above optimum range. It becomes more saline and it is raised to higher altitude. Low level of dissolved oxygen, which can stress fish, is due to the following conditions: cloudy weather, raining, especially prolonged raining, plankton die-offs, heavy stocking of fish, high feeding rate or ad libitum feeding or feeding in satiation, and lastly is the high organic load. Next, let me enumerate the signs that the fish will show if dissolved oxygen reaches low levels. So here are the following. First, we will notice that the fish are not eating and acting sluggish. It is gasping for air at the surface or surfacing. Group near the water inflow, slow growth, outbreaks of disease and parasites. So here are the management techniques in preventing problems with dissolved oxygen depletion. Monitoring of dissolved oxygen at critical times at dawn down to 6 a.m. Avoid overstocking. Avoid overfeeding. Sliding rule of feeding should be adopted, like for example from higher to lower rate. Avoid over-fertilization in case of ponds. Installing of aeration in case of ponds also, and keeping water circulation. Dissolved oxygen in the water can be expressed in two ways: the absolute concentration or relatively concentration, and measured by titration using Winkler method, by electronic instrument, yellow spring instrument, or by reagent chemical substances with the use of Hatch kit.
For 6 is pH. Measures degree of acidity or basicity alkalinity of a solution. indicates the ability of the solution to give up hydrogen ions or acidic, or take up hydrogen ions or basic. For option 1 equation, pH is equal to open parenthesis negative close parenthesis log open parenthesis H plus close parenthesis. For example, pH is equal to negative log open parenthesis 10 raised to the power of 7 close parenthesis is equals to 7, or pH is equals to negative open parenthesis log 1 times log 10 raised to the negative 7 close parenthesis is equal to negative open parenthesis log 1 plus 10 raised to the power of 7 close parenthesis is equals to negative open parenthesis 0 plus negative 7 close parenthesis equals to negative open parenthesis negative 7 close parenthesis, and it is equals to 7. pH is equals to the negative logarithm of its H plus concentration. pH scale ranges from 0 to 14, 7 as neutral, less than 7 minus 0 is equals to acidic or sour. Greater than 7 to 14 is equals to basic bitter. pH of natural waters are found to be high during the day and low at night. CO2 plus H2O is equals to H2CO3 or carbonic acid. Check the pH at daybreak and afternoon to get a profile of the diurnal shifts in pH. Water with pH values of about 6.5 to 9 at daybreak are best for fish production. Slow growth in waters with pH values between 6 and 4, and death may occur at the pH values of 4 down to 0, and at pH 11 up to 14.
Alkalinity. It is the ability to accept hydrogen ions or to neutralize acid, and it is a direct counterpart of acidity. Total alkalinity. It is the total concentration of bases present in the water expressed as milligrams per liter or parts per meter of equivalent calcium carbonate. The dissolved compounds producing alkalinity may be divided into two groups. First is those producing alkalinity alone, such as sodium carbonate, sodium bicarbonate, potassium carbonate, and potassium bicarbonate. Second is those producing alkalinity in hardness, such as calcium carbonate, calcium bicarbonate, magnesium carbonate, and magnesium bicarbonate. Carbon dioxide readily soluble in water and forms carbonic acid. During the day, carbon, and at night, there is carbon dioxide production and the pH is low. For waters with total alkalinities less than 20 milligrams per liter is equal to limited amounts of available carbon dioxide are present. Waters with total alkalinities of 20 to 150 milligrams per liter is equal to suitable quantities of carbon dioxide. At low alkalinity, fish are sensitive to some toxic pollutants. Total alkalinity is measured by titration method or by reagent chemical substances with the use of Hatch kit. Optimum levels of total alkalinity is at the range of 20 to 300 milligrams per liter.
So what is total hardness? Total hardness is a measure of the total divalent cations or ionic species with a charge of +2 predominantly calcium and magnesium ions expressed as milligrams per liter calcium carbonate. The hardness-causing compounds are not identified individually. Hardness values reveal that the hardness is equivalent to that produced by the calcium carbonate. Sodium and potassium compounds do not produce hardness. The carbonate and bicarbonate salts of sodium and potassium produce alkalinity. The calcium and magnesium salts account largely to the hardness of the water. Calcium and magnesium bicarbonates cause temporary hardness to water. The term temporary is used because upon boiling, the bicarbonates change to carbonates and part of the calcium and magnesium are precipitated. Water with temporary hardness are called soft waters. Permanent hardness is due mainly to the soluble calcium and magnesium carbonates and salts of inorganic acids. Water with permanent hardness are called hard water. Total hardness is measured by titration method or by reagent chemicals with the use of the hack kit. As in the total alkalinity, the desired levels of hardness should fall within 20 to 300 milligrams per liter range. Ammonia is the second gas of great importance next to oxygen in fish culture. Its significance to good fish production and fish hatchery is overwhelming. In a body of water, large or small, high ammonia levels can arise from overfeeding, protein-rich feed, or excess feed decays to liberate toxic ammonia gas, which in conjunction with the fish's excreted ammonia with urea and other foreign wastes may accumulate to dangerously high levels under certain conditions. Fortunately, ammonia concentrations are partially curbed or buffered by conversion to the non-toxic nitrate ion by nitrifying bacteria, which can be grown on most any coarse medium such as rocks, oyster shells, or plastic chips containing calcium carbonates. Additionally, ammonia is converted to non-toxic ammonia ion at pH below 8. As long as pH is 8 or lower, ammonia levels of up to 0.5 parts per million will be safe. The presence of both ammonia and ammonium ion in the water is known as the total ammonia. The levels within which the following forms of ammonia are maintained for hatchery purposes are ammonia, which should be less than 0.1 parts per million as the nitrogen content of ammonia. Ammonium ion, which should be less than 1.5 parts per million as the nitrogen content of the ammonium ion. For total ammonia, it should be 1 to 2.5 parts per million.
Nitrites. Nitrites are formed from the partial oxidation of ammonia by nitrification of the bacteria called Nitrosomonas. These are under aerobic conditions. In some conditions without the presence of oxygen, these nitrites are produced from the reduction of nitrates by the action of denitrifying the bacteria called denitrificans. These nitrites may be found in waters, but they usually exist in low concentrations. Nitrites should be maintained within the limit of 0.1 parts per million or lower for hatchery purposes. Nitrates. Nitrates are the fully oxidized form of nitrogen that is frequently present in water. These are produced by nitrifying bacteria known as Nitrobacter from nitrites, aerobically or in the presence of oxygen. A few bodies of water may also include nitrate nitrogen due to the addition of chemical fertilizers. Carbon dioxide. Natural waterways have a high level of carbon dioxide, which is a product of the aquatic life's respiration. During the day, photosynthesis in aquatic vegetation produces oxygen and consumes carbon dioxide. The dissolved oxygen and carbon dioxide have an inverse relationship, that is, when the carbon dioxide is low, the dissolved oxygen is high, and vice versa. The water's carbon dioxide content may serve as a gauge for successful or unsuccessful photosynthesis process. High values during the day suggest that suboptimal photosynthesis. This also suggests that the carbon dioxide is not being adequately absorbed by the phytoplankton. It also indicates that these plants are not sufficiently producing food and oxygen, and at the same time, low levels of carbon dioxide might be a sign of optimal photosynthesis.
Heavy metals. In case they are present in the aquaculture system, they should be at the limits or levels lower than presented below as follows. For the copper, 0.006 ppm or parts per million. For the lead, 0.03 ppm, cadmium 0.003 ppm, mercury 0.002 ppm, and for the nickel 0.100 ppm. Next is the zinc 0.05 ppm, for the chromium 0.1 ppm, for the iron 0.5 ppm, for the manganese 0.01 ppm, and for the last one, the polychlorinated biphenyls or PCB is 0.002 ppm. Pond management. It needs regularly change at least 25 to 30% of pond water during spring tides, full moon, and new moon. It needs to maintain a water depth of at least 50 to 75 cm for milkfish ponds and 80 to 120 cm for shrimp or sugpo, rabbitfish or siganid, malaga, samaral, and saline tilapia ponds. Use pump to increase pond water depth when tidal current is low. Fertilize the pond only after the last water exchange during spring tide. Maintain cleanliness of the sidings of dikes. Regularly check dikes and patch up the leakages and seepages. When we say dikes, it gives the necessary volume of water impounded and form the actual pond. Next, regularly check the gate screens and slabs. Observe the health condition of the stocks. Take immediate action if there are signs of abnormalities and diseases. Cage or pen routine management. In monitoring water quality, the following are need to be monitored. We have here the dissolved oxygen, temperature, pH, ammonia, nitrite, and turbidity of water as measured by a Secchi disc. The Secchi disc is used to measure water transparency or turbidity in bodies of water. The disc is mounted on a pole or line and lowered slowly down in the water. The data on dissolved oxygen and temperature are the most valuable factors that should be collected. Time of monitoring or collection of data should be daily and at times when they are likely to be highest and lowest. Example, the dawn or early morning, midday, late afternoon, and at the slack tide in the case of dissolved oxygen, temperature, and pH. Monitoring of water quality is of great importance to those cage farms, which are intensively managed and which have a high production with respect to the size and nature of the site.